Hello students, it's Dr. Sansom here. I want to do some calculations with light today. So there's a couple of equations that we need to be aware of and also some concepts that we need to be aware of. I'm going to start with a sort of brief introduction to waves. So you're going to be subject to my really bad drawing here. But let's say I have one wave that looks like this, and then I have another wave and it looks like this. Okay, so we're going to talk about a couple of things that are similar and different here. So first, they're both waves. We can see that because they are oscillating, going up and then going down and then coming back to the same place. When we're talking about waves, there's three main characteristics we're going to care about, which are the wavelength. This is represented by the Greek letter lambda. It's this guy. It looks kind of like an H, I guess, but Greek letter lambda. And the wavelength would be from trough to trough or peak to peak, or in this case, just what I've drawn here from the beginning where it was at 0 to where it cycles back again to the same spot. That's like one wavelength. On the second wave that I drew here, this is like one wavelength from here to here. So it has a shorter wavelength than the first wave that I drew. That's the first thing that we're going to talk about. Second thing we're going to talk about is nu. This is the Greek letter nu. It's the symbol for frequency. And frequency is the number of times per second. It has units of per second or hertz. Hertz and per second are the same. And I should say also wavelength would be measured in meters. Typically for light, we're using nanometers. So the frequency is going to be how many cycles we have per second. So assuming that the distance represented from the start to the end of this wave is 1 second, this would have a frequency of 1. And if this one also went for 1 second, second wave would have a frequency of 2. Just 2 complete cycles per second. Okay. Third thing, we've got, I'm going to put C here. This is the speed of light. Not all waves go at the same speed, but for light, they do. And it has the value of 2.998 times 10 to the 8th meters per second. So that's the speed or velocity. Now these three things are related. So there's an equation, C equals lambda nu. That's a nu. Nu's kind of hard to draw. So anyway, C equals lambda nu. This is useful because we can now, if we know lambda, we can find nu and vice versa. Now, there's one other thing that I want to talk about here. I guess there's a couple other things. So a couple other things to point out here. You noticed, I'm sure, that the top wave has a longer wavelength than the bottom wave, and also it has a lower frequency than the bottom wave. So these are inversely proportional. Lambda and nu are inversely proportional. When I have a long wavelength, that means I have a low frequency. If I have a short wavelength, that means I have a high frequency. Okay. I also want to talk briefly about amplitude here. So the amplitude is just the distance from the baseline to the peak. And you can see this bottom wave has a lower amplitude. With light, if we're looking at light, the brightness of the light is related to the amplitude. So sometimes we also use the word intensity with respect to light. Okay, that's just a sort of a brief overview. We've got one equation here, and we've got one concept. Lambda and nu are inversely proportional. Now, the other things that we need to know about light, we want to also consider energy. And it turns out that energy equals h nu, where h is Planck's constant, or hc over lambda, just substituting in using our first equation. And h has the value of 6.626 times 10 to the minus 34 joules seconds. And this just tells us how light can be quantized The smallest chunk of light would be 1 h nu. And it could be in multiple packets of that. Okay, so these are our two equations. There's one more concept that we have to talk about, which is the way energy is related to wavelength and frequency. Energy is directly proportional to frequency and inversely proportional, my writing, to wavelength. I'm trying, you guys. Okay. So, in other words, if I have a long wavelength, that's like a large value for the wavelength, because it's in the denominator over here, that means my energy is going to be small. But in contrast, if I have a high frequency, because it's up here, my frequency increases, my energy is going to increase as well. Okay, so those are my two kind of equations and two big concepts. Let's do a couple of practice problems. So first problem, I'm going to say, I want to know what's the energy of light with a wavelength of 700 nanometers. 700 nanometers is like the edge of the visible spectrum on the red side. So I want to know what's the energy of light with a wavelength of 700 nanometers. So what are the things that I know? I know E equals h nu, and E also equals hc over lambda if I substitute in for nu. And I know the wavelength here. This is my lambda. So I think I'm going to use this second equation. So E equals 6.626 times 10 to the minus 34 joule seconds times the speed of light, 2.998 times 10 to the 8th meters per second, divided by my wavelength. Now my wavelength actually has to be in meters because my speed of light up here is also in meters. So I'm going to have to convert from nanometers to meters. Now, it's really easy to do. I just say 700 times 10 to the minus 9th meters. It's not proper scientific notation. If we wanted to do that, we'd do 7 times 10 to the minus 7th. But it's easy to remember. You just multiply by 10 to the minus 9th. So we've got all of our values here, and we can calculate, and I get 2.84 times 10 to the minus 19th. Joules. Okay, so that was fun. We know the energy of our photons of light, of our red light. What if instead of calculating the energy, I just want to know what's the frequency? Of light with the same wavelength, 700 nanometers. Well, I'm going to use my equation C equals lambda nu. I know C and lambda, so if I solve for nu, I get C over lambda. So I can plug in here 2.998 times 10 to the 8th meters per second, and I'll divide by 700 times 10 to the minus 9th meters, and I get 4.28 times 10 to the 14th. My meters are gone, and I just have per second left. Okay, that is my frequency of light. One of the things that I want you to pay attention to is like what magnitudes are normal here. We're dealing with like numbers that can be very large or very small depending on what we're talking about. So keep an eye out when we're looking at energies, usually 10 to the minus 19th, maybe 10 to the minus 18th joules. When we're talking about light wavelength, we're usually on the order of nanometers. And if we're talking about frequencies, 10 to the 14th, 10 to the 15th, 10 to the 16th, those are all kind of normal frequencies for light. Okay, that's everything about our light calculations. I hope that's helpful, and I hope you have a great day.